So today I want to do three things. So I'd like you to, I want to do three things, and what you take away is, of course, up to you, etc. But I do want to describe what a galaxy is and what dark matter is and why we believe that dark matter is there. That's kind of the first thing. And if that's all that you get from it, I think that's probably a pretty good thing already. The second is I want to describe how we think of galaxies in a dark matter dominated universe. So what do we think of galaxies now that we think that most of the universe is dark matter? And then finally, I wanted to describe a little bit what type of research I do into trying to understand how the galaxies that we see talk to the dark matter that we think is most of what is. So that's what I will be attempting to be doing. It may or may not work. We will see. All right. So first of all, and this is, now, as when all of us are encountering a subject for the first time, one of the first places we go, for any of the students in the room, it cannot be the last place you go, is Wikipedia. And so this is the Wikipedia first line of what is a galaxy. A galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas and dust, and dark matter. And this kind of jives with how many of us think of galaxies, and this is a particularly beautiful image of a particular galaxy taken by Hubble Space Telescope. And so it's really, this is the kind of quintessential idea of what we think a galaxy is, or of what we think of when we think of a galaxy. This galaxy is a little bit smaller than the Milky Way, just for reference. So we're rather larger and more grandiose than this galaxy, but this is a very nice one. But galaxies are, so people are very diverse. Galaxies are shockingly diverse. Here I'm showing you a variety of galaxies. There's a factor of 1 billion in the size or in the mass of galaxies, right? So it's like if you went out and had people, and you had people that were like you and I, for example, but you would also have people that were much smaller than a grain of rice, and that was completely reasonable and normal, right? And in fact, most people were much smaller than a grain of rice. And then there were a few really big people, like you and I. That's what the universe is like. And there's many different types of galaxies too. So let me just show you. This is one of the faintest. Hold on, where's the pointer going? I always do this. All right. This is one of the faintest galaxies that we know of. So these galaxies are actually so faint that you see right through them. You have to find them by counting individual stars. So these little tiny green dots that nobody can see probably, sorry, are the 1,000, or are the brightest of the 1,000 or so stars that we think live in this galaxy. It's called Wilhelm I. It was a relatively recent discovery, right? We did not know galaxies came so small until about 10 years ago or so. And we're still very much struggling with, well, what is a galaxy now that we're thinking about? Now that we know that galaxies can look like this. Oh, thank you, that's even better. It makes it slightly less invisible, right? Right. This is a relatively bright, very faint galaxy. This guy is, it's called the Fornax dwarf spheroidal. It's a factor of, hold on a minute. I should have done this math before I came in here, rather. It's about a factor of 100,000 fainter than Milky Way. Right? So this has something like 100,000 or a million stars in it. And you can actually kind of see it. It's, you can't see it with the naked eye, but with a powerful telescope you can see it. This is a galaxy somewhat like the Milky Way, maybe a little bit smaller. And this is one of the largest galaxies in the universe. It's M87. It's a central galaxy, the Virgo cluster of galaxies. And it has around 1 trillion stars in it. Right? So we've gone from having a few thousand stars to what is likely to be well over 1 trillion stars in this galaxy. So one of the things that we won't even talk about today, which is kind of sad, but is really one of the central things that drives our efforts to understand galaxy formation are what leads to this diversity in galaxy types? How can you have a universe in which most galaxies can be so very small, but then you have some truly enormous galaxies also? What can lead to this diversity? All right. So this is getting you a little bit up to speed with what galaxies are. I want to start dealing with dark matter now and what we think dark matter is like. And as you will find out, we know relatively little about dark matter. There's a really excellent, how many of you know about PhD comics? Just like the, okay, not many, okay. So there's this wonderful institution called PhD Comics. It's a group of people, they're at CERN, and they actually are, they spend a lot of time trying to communicate science in a way that's accessible to folks. They did a very nice introduction to dark matter, so I wanted to kind of give this to you in part so you can look at it yourself. You can look it up online when you're bored. It's about 5 minutes long. We're going to be looking at about 2 or 3 minutes of it. All right, so let me start this. Now, the sound isn't very good, I'm sorry. So they actually record this in the cafeteria at CERN. And so you hear people in the cafeteria at CERN. All right. Sorry.
We've been studying matter for a couple hundred years, right? Refined understanding of chemicals, and all of a sudden we discover that all that work we've been doing is on like this tiny fraction of what the universe is made out of. It's like you've been studying an elephant's tail for 200 years, and you discover it's only the tail. If you look at what is the universe made out of, like a pie chart, 5% of it is stuff we know. 20% of it, dark matter. 75% of it, we have no idea. Dark matter is 5 times as heavy as all the matter we know about. That's the familiar kind. Stars, planets, asteroids, etc. There's these huge, massive blobs of stuff out there. It's huge. It's everywhere. We just can't really interact with it very much. There's 4 major ways that things interact. There's gravity. If you have any mass at all, things get attracted. There's electromagnetism, which is, like 2 charges repel each other. And that's the major force that you actually feel. If I press down on this table, the reason the table doesn't get crushed or pushes back is that the molecules inside the table are holding tight on each other electrically. There's another force called the weak nuclear force. It's like electrostatic forces, but it's much, much weaker. And then there's a 4th force, which is called strong interactions. It's inside the nucleus. It's what binds the nucleus together. All of these things are just descriptive. We don't understand why any of these things happen. This is just like a summary of the things we've seen. It's like botany. Here's what we've observed. And so far, we can explain every experiment in terms of these 4 kinds of interactions. Dark matter has mass, but does not have electrostatic interactions, which is why we can't see it. It doesn't reflect light or give off light. For a while, people thought maybe dark matter was just a lot of neutrinos. But it has to be an enormous number of neutrinos, like a ridiculous number of neutrinos.
There's 2 classes of ways that we have evidence for it.
One way you see dark matter is things don't spin the way they should if there's only normal matter. There's obviously big clumps of normal matter.
There's another one that's really...
Okay, let's stop this right here. I want to spend a couple minutes unpacking this first way that we think we know dark matter is there. It takes a little bit, they say, oh, because of how galaxies move. It's like, okay. I'm going to try and tell you a little bit more about how that actually works. Okay, so the first thing I need to do is to help us just kind of get an idea of the type of observations that one makes in order to play the game of trying to figure out how matter in galaxy moves. So we have the U of M demo lab. The physics demo lab is awesome. I love them all very much. And they do, I know, thank you. This is good. Thank you. And they do a bunch of very useful things to try and help this stuff become rather more real and visualizable. So what they've done is they've put, as you can see, a few light bulbs on a stick and on a rotor, which seems like, okay, well, that's terrific. But what we can do is it can help us visualize how we observe, or one of the ways in which we can try and observe mass moving around in galaxies. So we had stars being an important part of galaxies, gas being an important part of galaxies. And galaxies, the material in galaxies rotates. And so this gives you kind of an idea of looking at something rotate. Now there aren't merry-go-rounds in parks anymore, which seems really sad. But this is an object that acts like a merry-go-round. So the middle, as you can see, hardly moves at all, even if I make it rotate fast, or really fast. They're going to get mad at me because it'll apparently fall off the table. I love this game. Anyway, all right, so this hardly moves at all because it's very close to the middle. This one moves, somewhat, it moves a little bit, and this one moves quite quickly. Now, there's a couple things about this that don't look anything like galaxies. One, it takes a galaxy about 200 million years to go around, and they said I needed to stay within an hour, so we couldn't wait for 200 million years for it to go around once. The second is, it's on a stick, and there are no sticks in galaxies, right? The gravity keeps the stars in motion, and they actually end up moving somewhat differently from this. What is another? But the manner in which the objects move is also quite different. So I'm going to have to draw, I was told that the graphs are bad news in this context. So I'm going to draw only a couple of them. Can you see over there, or did I just draw the axis in the wrong spot? Okay, I'll label it over here so you can see what's going on. This is the velocity, right? And then this is the distance from the middle. Is the writing big enough for you to see? Yeah. Good, we're good. All right. And this particular experiment has not much motion in the middle. As you go further out, you get more and more motion. And so you draw a line like this, and this is what something on a stick would look like. This is how you move on a merry-go-round. This is another big difference. We can't wait around. So tenure is a wonderful thing, but a career is only 20 years long, so you can't watch the stars go around. Here, you just watch the stars go around. What you actually have to do is to look at the shifting of the wavelength of the light. So as this object is coming away from you, it turns out that its light is stretched out a little bit, red-shifted, and as it comes towards you, the light is compressed a little bit, blue-shifted. And so you actually use the red shift and the blue shift of the light to measure it in practice. You don't wait to watch it go around, because that's longer than a graduate student's or a professor's lifetime. Okay, so this is how this moves. Let me show you this now. This shows you, this is not how objects move in response to gravity, somewhat disappointingly. But CVID, right? Good. Okay. Oh, don't turn the lights down too much, sorry, because you need to see this. Okay, so this is, these are terrific, by the way. And so if you feel like feeding money to it later, then fine. I'm sure Saturday morning physics would appreciate it. Unfortunately, I have only pennies, so they're going to be really cheesed off. And they're Warren's pennies, I think, anyway. Thanks. All right, but you are familiar with these. And so, the idea is you put a penny in, it goes round, but then because of friction, it goes further and further down, but it rotates faster and faster as you head towards the bottom, right? So these are just terrific fun. So I end up spending a lot of my money at museums like this. Yay. I don't know what you guys are doing. I'm having a great time. All right. So this kind of motion actually looks very different from the type of motion we have from this machine, right? This machine, you had the amount of motion getting faster as you went further out. The other one, you actually ended up with the motion being quite fast at small distances and smaller as you went out. Oops, that was a very big data point. It's because the penny knew it was going to die, so it's like, no! All right, so this is how that moves. This is how planets in the solar system move. Right, so why I wanted to show you this is because this is how, this is kind of how objects move, or gives some idea of how objects move in something like the solar system, where you've got a big sun in the middle, and then lots of low-mass planets just kind of wandering around. Right, as you end up with this type of plot. Galaxies. Now, galaxies, as you will know, sorry. All right. Oops, not the Blu-ray. Galaxies are spread out. They're not like the sun. Oh, it's kind of a mess. You can leave, well, okay, as long as you can see this, we're all good. They're kind of spread out. So it's not that there's all the mass in the middle, but they also don't go on forever. And so we would expect And so you can do math if you feel like it, and most of us don't. And what you expect for a galaxy is that it would have a trend something like this. The mass gets bigger as you go further out, and that more than compensates for the drop in the drop in the gravitational pull from things that are far away. At some stage, the drop in the gravity is the same as the growth in the matter, and then eventually all the matter is more or less inside, right? If you reach towards the edge of the galaxy, then you more or less follow what you'd expect for having all the mass in the middle. Okay, so this is what we expected to see. All right, go ahead.
Would that have anything to do with
Thank you for being the first questioner, by the way. I appreciate it.
conservation of angular momentum? Would that have anything to do with conservation of angular?
Let's talk about angular momentum later. This is a great question. I love angular momentum very much, but we'll do that later. So the answer is yes and no. Okay, so let me show you the first bit of evidence. Right? So remember, this is what we expected to see. This kind of yellow line, which is nice and yellow, so Warren doesn't have to turn it up. I'm just doing this to play with Warren's head. It's awesome. All right, I love this game. All right, but this is what you actually observe. All right, this is what you expected from the visible disk. This is what one observes. This is M33 rotation curve. That's what you pick up from the starlight. You can also see very faint or very diffuse gas at the edge of the galaxy, and that does this. So the rotation does not slow down towards the edge of a galaxy. Right? This is enormous. We had no idea. I mean, one, we had no idea this was going to happen. But two, the thing that, gravity is the only force that can cause or that can contribute to the motion of stars on such large scales, stars and gas on such large scales. And so this was telling us there's more mass there. And so there's more mass in this system. Remember what drives, I won't mess with Morin's head anymore, sorry. But what drives this peaking and then going down is that you run out of material and then it just starts to decay as you'd expect from most of the mass being in the middle. The fact that this continues it goes flat or it goes up is telling you there's more mass there. Right? This is an enormous deal. Okay. Okay, we're going a little bit longer than I thought, but that's okay. So there's a second thing. I'm not going to restart the PhD comics, I'm sorry. But just to remind us of where we're at. Right? So we now have, from this kind of experiment, the idea that most of the mass in the universe is in this form of dark matter that we don't really understand. We do know what it does, but we don't know what it is. Right? And it was kind of nice that they pointed out, botany or whatever. Like, we know what things do, kind of. We've characterized it, but we don't know why it does it necessarily. So, in some sense, the way we think of dark matter is descriptive now. We think we know what this does, but we do not know what it is or necessarily why it does it. So it is most of the material in the universe. It feels the force of gravity, doesn't feel the electromagnetic or the strong force. It may feel the weak force. We hope so, because that's the way that our friends who attempt to find dark matter would find it. And then this is one of the pieces of evidence for the way that stars and gas move in galaxies. There's a second way, and it's actually about the same physics. So here you're looking at stars and gas moving in galaxies. You can also watch light move in galaxies. Light goes fast, and so instead of orbiting it, it just gets a little bit deflected. It goes pink, and has a little bit of deflection. So let me show you a demonstration that kind of shows you the principle of gravitational lensing. So this is a picture. I guess it's one of the Hubble deep fields. It might be the ultra deep field. But this is kind of a representative background of galaxies. And we have the bottom of a wine glass. And it turns out that this actually gives a deflection that looks a lot like gravitational lensing. So if I put a blob of matter, if I could just get a blob of matter you could not see and put it in the middle of the image, it would cause the light that is coming from behind from behind that blob of mass to bend around it. You would actually see two images of the same thing. And so, if the if the galaxy is over here, there's this blob of matter. There is us. We'll draw the traditional kind of physics eyeball. The light that was heading in this way and the light that was heading in this way, they should have gone to other eyeballs over here if they exist in the universe, which is a really interesting question that we will not talk about. As most interesting questions, we never talk about any of them. It's kind of annoying. Yeah, I really want to know if we're alone or not. The light bends around this, though, and we end up getting light that was destined for other directions but ends up coming to us instead. It's called gravitational lensing. So this here is showing us what gravitational lensing does. And so when you can see when you're far away from it, you distort the images somewhat of galaxies. But if you get it just right, you can end up with full rings where the light that should have gone in any direction around the galaxy all gets focused on you. Right? This is very, very powerful. We have people at the University of Michigan who study this to try and work out, one, what the distribution of mass in the galaxies, in the big mass blobs, these things. And the second is to actually use it as a telescope to get more light from these objects, because these objects are very faint, they're very far away, and it makes them easier to study. So let me show you a picture of one. If I was projecting the right thing, which I wasn't, sorry. Okay, so this is a real system. It's awesome. It has a really boring name, so it should be called like the smiley face cluster or something, but instead it's SDSS J1038 plus 4849. There are two massive galaxies which contain a lot of mass. They're in the middle of a cluster of galaxies, and it bends the light from background galaxies into a shape that looks like something, which is kind of cool. Right? But there are many, many examples of this. And so you can use this technique to find out where stuff is in the universe. All right, so when we want to figure out, so one of the things that we should be very stressed out about is, okay, hey, the stuff in galaxies moves like, thanks, moves like this instead of like that. Maybe that's just the law of gravity being wrong on really large scales. It could totally be the law of gravity being wrong on very large scales. These are on scales that we've never probed before. So it's possible that that's how the universe works. But there's a really good way to test that. The main idea there is, if it's the law of gravity, so if everything that we know, if this stuff, and you and I and the sun and gas between the galaxies is all that is, then we should go to a system where we expect the dark matter to be in a very different place from the normal matter. This system up here is one of those systems. It's one of the cases where you have two galaxy clusters. They've collided. Galaxy clusters, they have galaxies in them that are stars, but most of their mass is in terms of hot gas. So when two of those clusters collide, the stars, for reasons that I won't explain, I'm sorry, largely pass through with very few interactions. It turns out stars are very spread out in the sky, and so interact mostly through gravity alone. The dark matter would do the same thing, but the gas would go and smash in the middle. And so the gas, which is most of the normal matter, should be in a very different place from the dark matter. So you can then use gravitational lensing, this stuff, to figure out where the material is. This red thing is where the normal matter is. This blue is where the mass is. The mass in the system is where the dark matter should be. It's not where the normal matter is. This is why we think it's dark matter. These are some of the most conclusive or compelling pieces of evidence that argue that it's not just that we've messed up our understanding of gravity on large scales, that it's actually a form of mass that we can't interact with using electromagnetism. Right? So I just wanted you to know that's why we think that most of the universe is dark matter. Okay. So there's other pieces too, but we won't talk about that. So the bottom line of this part is, that most of what is dark matter. I love science. We understand Most of what is in terms of mass is dark matter. Most of what is in terms of mass and energy in the universe is dark energy, which we understand even less about. It's really exciting. So 96% of all the mass and energy in the present universe, we have no idea. We have ideas of what it does, but we do not know what it is or why it does it, which I think is awesome. That's a wonderful statement about science, right? Because we're just trying to figure out what is. We're just trying to learn about it. Who should say that we should know a lot about the universe? Right now, I think it's tremendously helpful to realize, hey, you know what? We haven't even reached 4% in terms of our understanding of the universe. That's like an F minus. We don't use Fs at the university. It's E minus, I guess, or something, right? I wonder if I'm allowed to give an E minus. For some of my students in the room, don't make me test it out. Right. Anyway, okay, so this is pretty cool. So what does this do to galaxies? What does this mean for how galaxies form? And in order to do that, one has to turn to simulations, simulate how galaxies should form. So you try and make these supercomputer simulations where you have the laws of gravity for dark matter. You have what we think dark matter might do. Then you put in normal matter and how we think that works on these kind of scales. And those are all approximations. So you try hard, you do your best. But there are parts of that that are going to be somewhat preliminary. And then you figure out, okay, this is how we think galaxies should form. We observe galaxies and then ask, do we see signatures of that? That's really the process in which I'm engaged as a scholar. Is I want to understand, does this kind of idea that dark matter drives most of how galaxies work, what does that actually predict, and can we test that observationally, even though we cannot see the dark matter? So let me show you a simulation in which the dark matter has been conveniently colored orange, which is very useful. Let me stop it for a second. So what we do is we start off, this is the Via Lactea simulation. It's from 2007. It's not a particularly young simulation, but they do have some of the best visualizations. So what this is this is just dark matter. Remembering it's most of what it is, it's fine to ignore the rest of matter at the beginning. And so this is, the universe starts off very smooth and with only little tiny inhomogeneities. So little dense pieces, little underdense pieces. But gravity is the ultimate capitalistic force. It's only attractive, and if I have a little bit more mass than my friends, I will get more mass because I have more gravity than everything else. And then I will get more mass because now I'm even bigger. Then I will get more mass and I will get more mass. And so the rich get richer and the poor get devastatingly poor. This is not at all a social commentary. I don't know why we have to act like gravity. Anyway, here we go. So this is a simulation where you started out with some just little blobs of dark matter. They keep on growing. They merge with each other into progressively larger and larger systems. And so as time continues on, and this is now about halfway through the history of the universe, about 7 billion years ago, you end up with these relatively large blobs of dark matter. They interact with each other. They grow, but at some level, a lot of the action is actually kind of done by the time you reach the present day. And so the early stages of galaxy evolution, you see a tremendous amount of merging in galaxy growth as these dark matter halos, they merge with each other and grow larger and larger, and that settles down towards the present day. So let me show you a snapshot from the end of this, from the Via Lactea simulation. This is what we think the dark matter might look like. It's very centrally concentrated. It's a relatively smooth distribution. It has a lot of lumps in it, right? A lot of these little lumps. Now this, of course, is what you see. Darn it. Why did we use all that supercomputer time? Right? This is what we see, right? We see galaxies. And the galaxies that we see, it turns out that the extra physics, right, paying attention to electromagnetism makes a big difference to how galaxy formation works. And so let me try and unpackage a little bit of how that actually works. All right. Here's your dark matter halo. We're going to leave this up for a second. So if we can turn the lights up a little bit, then we need to turn the lights up a little bit. I'll move this over because I don't want to destroy anything unnecessarily. So I'm going to do a demonstration where we have a bowling ball, and it's trying to show us something about the conservation of energy, right? So you want to ask about conservation of angular momentum, which we'll do in a minute, but right now we're talking about energy, right? So now one of the perks of this job is you get to do things like this. I love this job. Okay, now, there's a little bit of friction in this. It should have come back and touched me in the nose, unless I pushed it, in which case I hope somebody is a doctor. It'd only be a broken nose, probably. Yeah, seriously. So there's a little bit of friction in it, which means it didn't quite come back to my nose, right? Instead of touching it, hope I didn't push it. Right? It came back here instead, so it's about an inch off or so, right? That's just because of friction in the system. So if this conserved energy, it would come straight up to the same point. Here it has a lot of potential energy, gravitational potential energy. Here it has a lot of energy of motion, kinetic energy, and then it gets back up to potential, kinetic, potential, okay? Dark matter, because it doesn't feel electromagnetism, it can't feel friction. Friction is all about electromagnetism. And so this distribution of stuff is what you expect when you have no friction in a system. But if you have normal matter with friction, messing with Warren's head again, then something very different happens. Okay, so we're going to try this. There you go. I really don't have to sweat this. I can even push it now. Now, do you notice anything?
Separation's getting bigger and bigger.
Yeah, it's not getting anywhere near as close. Energy isn't being conserved. Where's it going?
Lost in the heat friction between all.
And you can hear it?
Yeah.
Swoop,
And sound.
swoop, right? So you're losing energy here, right? Because there's a little bit of friction. So normal matter loses that energy. And the fun thing about normal matter is it loses a lot of energy. And so it will act quite differently. You expect it to be closer to the middle, and a lot closer to the middle, than the normal matter, or than the dark matter. This is the distribution. This is what we think galaxies look like in this dark matter context. So these little things are real galaxies. You expect the largest dark matter halos to host visible galaxies, only the very largest ones for reasons that I will not explain. Sorry. And for the scale of the galaxies to be much, much smaller than the dark matter halos, right? And this makes another really important difference. So not only are they smaller because you've lost energy, but because when I collapse, if I started off with a little bit of angular momentum, just a little bit of angular momentum, when I collapse, I end up with a lot of angular momentum. I end up with a tremendous amount of spin. And so this is why I end up in a disk galaxy. You ever wondered why galaxies are mostly disks, like spiral galaxies? It's because they did a lot. It's actually telling us something very, very, very deep about how galaxies form. It's telling us that they lost a lot of their energy. They collapsed, but they kept their angular momentum. And so that means they can't collapse this way, so they have to collapse the only way that they can, which is into a disk that then rotates. Right? Most things in the universe, or many things in the universe, are little disks that rotate, and that's why. It's the same fundamental physics in all cases. Okay. So, let me show you a simulation. It's going to have to get dark for this one. Let me show you a simulation of what we think galaxies actually do. This is a simulation of a galaxy that's going to form actually in a really enormous galaxy like the one that's in the center of this cluster we talked about earlier. This is what we think the stars look like in the simulation. This is what the gas looks like in the simulation. One thing I want you to think about right now, remember these earlier dark matter simulations, you had all this stuff everywhere, right? The whole thing was orange. Here, the stars really are only in the very center of the systems. This is exactly what we expect to have happen. The gas and the stars, the gas, it experiences friction, it collapses right to the center, and has a little bit of rotation, which is why they're mostly, well, some of them are disks. This dude's a mess right now. But this one's a little bit of a disk, and you'll see some disks later. Now, the disk, the gas does some fun stuff. This is a completely another talk as to how this gas acts. I'll let you watch the movie for a minute. This is terrific fun. Now, something you'll notice is these galaxies are interacting with each other. That's mostly because of the dark matter behind them. It looked like this galaxy just appeared, and that one just appeared. Those just came in through the visualization window. They had formed somewhere else, but they just came in through the box that they're projecting right now. This is going to be a 5-galaxy merger, which is tremendous fun. The gas is rather more extended than the stars, and you can actually see these outflows of gas. We think that big galaxies, the black holes in the center of them blow out gas and stop them from forming stars at late time. It's this thing called AGN feedback, which if I talk to you again, it might be about that instead, because it's also terrific fun to think about. Right? And so one ends up with a galaxy, in this particular case, just one galaxy, right? So all of them merge together into just one galaxy at the present day. But it's relatively compact compared to the dark matter distribution that made it. Okay. So this is the illustrious simulation. I'll let the credits come up because these simulations are actually very, very hard. These are millions of dollars worth of supercomputer time, right? These are very hard problems to solve. And it takes a group of really some of the most talented people in the world to actually get this stuff right. Or to get towards a plausible answer. Okay, let me show you another movie. I have to do it this way. This is to try and give the idea, if I can find my pointer. There you go. This is to try and give you the idea of if I have galaxies, that there are many different ways to grow a galaxy. So let me just start this movie off. This is 24 dark matter halos, right? So we're looking at dark matter. Now it's blue instead and purple and things just because you can color it any way you like because actually it's dark. So they thought this was prettier than orange. And so we'll look at these 24 different dark matter halos as they evolve. Okay. So they're all collapsing in kind of similar ways, but you can see that their interaction histories are somewhat different. Some of them have more interactions. Some of them have them quite late. This one had quite a late interaction. This one's still interacting. This one's interacting right now. This one is going to do a lot of growth right at the end. Okay, so let's go back to the beginning. How do I replay? Pointer. There you go. Let's replay. Okay. So what I want you to take away from this is that just because of differences in the initial distribution of stuff, right? Because no two patches of the universe are alike, I end up with very different histories of how these things form. Okay? Now this must make a difference. All right, remember I was telling you that galaxies are really diverse and different? All of that diversity, there's one set of laws of physics, hopefully, but there's lots and lots of different initial distributions of matter. So all of that diversity comes from, not this, but that. Comes from the difference in initial conditions. Right? So if we want to solve galaxy formation, we actually need to figure out how these initial conditions talk to the properties of galaxies we see, but we can't see the dark matter. So we're stuck. Right? This is a really sticky problem. This is one of the reasons why galaxy formation is such a hard field. Go ahead, please.
Okay, you guys saw It's equal something, but why did it slow down at the end?
All right, so thank you. This is a good jargon check. I really appreciate it. This Z, this is called a redshift. Remember, I was telling you that when we observe the motions of stars and galaxies, we actually observe the shift in the wavelength of light. So the universe expands. And so as light travels through it, it gets stretched out. So it'd be kind of neat. It's like I start out at this end of the table like this, but then I get stretched out as I head towards the other end of the table, which would be interesting to watch, but uncomfortable. But that's what happens in the universe. You start out with short wavelengths of light. They get larger as they propagate throughout the expanding universe. Go ahead. Dark matter doesn't, or we think, I mean, look, how much do we know about dark matter? Not much. So it's an interesting process. So we've been thinking about dark matter as a community for about 40 years. I'm 40 years old, so obviously I wasn't thinking about it for all that time. But you can put in, so what people tried out is lots of different, like, hey, I wonder if it feels electromagnetism. What if it feels it just a little bit? What if it feels a strong force? What if it, you can make different assumptions about how it might act, simulate what it should do, and then you end up with a bunch of predictions. And so some of those predictions end up being completely wrong, right? Just completely, totally wrong. Just let me stop this because it's going to get distracting, sorry. It is pretty. So those predictions can be very, very wrong. And so then by a process of elimination, you can work out, okay, if dark matter felt friction, would it look anything like the universe? The answer is no. You actually need most of the mass of the universe to be in this very extended state. Remember, we only saw dark matter at the edge of a galaxy, not right in the middle, right? It's much more towards the edge. And if you go out, you can actually tell that it continues out a long way beyond the edge of a galaxy. That only happens if dark matter doesn't experience that friction. So that's showing you a little bit under the hood. I mean, it's somewhat of an oversimplification. We can talk about it later if you wish. Are you as happy as circumstances allow? Okay, good. All right. So I worry about this because I want to know how galaxies form and why they form the way they do. But it's mostly caused by diversity in dark matter growth histories, and I can't see the dark matter. Now there is, I actually realized I should have shown the other YouTube, which is up here. Okay, oh boy. Okay, so what I'm going to show you is, so there's a dark matter halo in the middle, and then there's a few galaxies that are going to come in. These are actually pretty small galaxies. So this is a simulation done by Andrew Cooper and a group at Durham. I had nothing to do with this. This is after I left. They all did this stuff, but it's good work, and it shows you how we might actually be able to get a handle on this. So what you can see, and let's make it full screen just for fun, is that as time goes on, because the dark matter halos, remember, they're growing and merging and doing all this fun stuff. And you realize some of them carry stars. Not all of them, but some of them do. And these stars spread out into a little halo a lot like the dark matter halo. Right? Now, it's not quite the same. It's rather more concentrated. And it's also rather more structured. And that makes sense because remember, the stars had collapsed right into the middle of the dark matter halo. And so they end up spreading themselves along actually very thin streams, etc., rather than in this very broad volume. But the process that leads to the growth of the stellar halo is the same process and has the same information, or some of the same information, that you had in the dark matter growth history. Right? And this is terrific. Right? It's really important because now we have a way to try and learn about what the individual formation history of a galaxy was. This is why I care about this. This is the only way I would maintain that we'll ever crack the nut of understanding how an individual galaxy grew. If we want to know how did the Milky Way grow, which sounds like that'd be fun to know that. I don't know if it'd be practical, but it'd be fun. This is the way we're going to have to do it. I think. I can't see another way around it. Okay, so let's go back to this. So then we predict this kind of thing. We expect a large stellar halo, call it a stellar halo, around a galaxy, where you have stars that were in these little dark matter halos, just in the middle of them, and they were spread out into a big distribution around it that tells you about how that formed. And they have the density profiles, so if you measure the number of stars as a function of radius and all the substructures, in principle, that's going to be able to tell us how those halos formed. Or at least that's the hope. I mean, there is information in it. Whether we can extract it is hard. So I'm going to show you the kind of observational part. So this is very theoretically motivated, just saying, hey, what is dark matter? Why do we... So I guess, one, dark matter. We talked about what dark matter was. Now we talked about, okay, how does galaxy formation work in a dark matter context? And now we're going to look at the outskirts of galaxies and try and figure out, okay, how much do we know now about these outskirts of galaxies? I hope that you care a little bit about the outskirts of galaxies now and realize, okay, that's why it might float somebody's boat, floats mine. So let's have a look at them. This is a galaxy, it's called NGC 5907. It's a Milky Way-like galaxy. It's edge on, right? So again, it lost a lot of energy when it collapsed, but it can't lose angular momentum easily, so it's a disk, a rotating disk. This is what it looks like. This is what it looks like actually until about 15 or so years ago, when technology got good enough to reveal this around it, right? This is a stream from a disrupting dwarf galaxy that got ripped apart while constructing NGC 5907, right? So it's approximately lined up. I tried pretty hard. It's not quite right, right? But you can see that, the disk doesn't get a tremendous amount bigger, but all of this stuff, all of this diffuse material is new, and we can kind of see that now. There are a number of such examples as this. David Martinez Delgado and Peter Van Dokkum have worked with actually relatively small telescopes. In Martinez Delgado's case, he works with people from, Jay Gabani, who's an amateur astronomer. He's quite an amateur though. He has a telescope with a diameter about this big, it's a robotic one. And he takes actually all of these images, and then David works with them to extract the science. But these are disrupting galaxies coming into the big main galaxies. Now, this doesn't give you, so this gives you the densest of the streams, but it does not give you the whole halo, right? You'd like to see this diffuse stuff too, because that encodes smaller galaxies that came in, or more ancient events, or different types of events that led to the growth of galaxies. So you have to use a different approach for this. And so my research and the research of my collaborators uses a different approach. So I want to show you how this works with something that's recognizable if it was ever clear in Michigan, which it is sometimes. And so this is the Big Dipper, or the Great Bear if you're into bears. So that part's the bear, front leg, back leg, tail, or the Big Dipper. And what we'll do is we'll start zooming in, and we'll get some idea of the kind of work that we have to do in order to actually look at the halos of galaxies. This is a galaxy that's called NGC 4244. It's this galaxy that's about 10 times smaller than the Milky Way. And as you zoom in on it, first through ground-based imaging and now through space-based imaging from Hubble Space Telescope, you realize that you're resolving it into individual stars. Right? So these are actual stars in that galaxy. They're 10 million light years away, as it turns out. Right? So the light from these stars is 10 million years old, which is already terrific fun. So before humanity was around. And you see the very brightest stars in this galaxy. So in fact, you infer something like, so for every little splodge you can see here, which is a star in that galaxy, you infer something like 10,000 or so stars that are much fainter than that you cannot see. But you see the very brightest of them. And for those of you who have difficulties with math, It's okay, because this part of astronomy is counting. I'm pretty good at counting, and I can say 1, 2, 3, 4, 5, 6. I can count those stars, and that tells you where this, how many stars there are in different parts of this galaxy. So this is my job. I get to count all day. It's awesome. All right. So let's go to the nearby galaxy. This is M31, the Andromeda Galaxy. This is, I know it's distance in parsecs, but unlike, a little bit over 2 million light years away. It's like 2.3 million light years away. It's a galaxy like the Milky Way, probably a little bit bigger. Right? So it's like our big friend. I'm assuming at some stage most of you had a larger friend. This is the Milky Way's larger friend. This is a very nice kind of ground-based image of Andromeda. We're going to change scale. This is the same ground-based image of Andromeda. This is the diffuse stellar halo around Andromeda. This took 150 nights, nearly half a year, of 4-meter telescope time from the Canada, France, Hawaii telescope. It was led by the PANDAS team. So they were working on it for about a decade. So they ended up with actually a large fraction of this telescope's time. And they made this map by individually counting stars around this galaxy, right? For 150 nights, and then working on the data for a decade. And what you can see is, that this richness of structure that we expected, it's there. The galaxy continues out 500 million light years. The size of this image is 500, no, did I get that wrong? No, 500 million would be stupid. 500,000 light years, which is still a big number. Right, galaxies, the main body of Andromeda is about 100, a little bit under 100,000 light years across. This whole thing is, so this is 500,000, so the whole thing is about 1 million across, 1 million light years. So light would take 1 million years to go from here to here. Right, this is incredibly diffuse. This is, each color shows the chemical composition of stars, which tells you something about the dwarf, where it came from. And so you can see these are, this is from a relatively big dwarf galaxy with lots of chemicals in it, lots of heavy elements. These blue ones are from from galaxies, smaller galaxies with less heavy elements in them. Right, so you can actually see the individual, the remnants. Right, so Andromeda is a messy eater. Right, it spreads its food everywhere. If any of you have had children and little babies, right, you know what they leave when you've fed them. I mean, once they're actually feeding themselves, there's usually this kind of halo of food around them and all over them. And we're just taking a picture of it. And we're saying, oh yeah, this person ate broccoli, this person ate carrots, this person ate pears, this person ate chocolate. What, Dad? Sorry. And so you can see what this galaxy ate to make it grow. Now, models, as we saw earlier, actually predict a great deal of diversity in stellar halos. So one of the things that I do, so this is another group that doesn't involve me, sadly. This is tremendous work. What we do is we actually study these galaxies. These are the kind of next most distant set of galaxies. Instead of being 2.5 million light years away, these are 10 to 30 million light years away. So they're much further away. The stars are a lot fainter. They're a lot harder to study. And because we couldn't do the easy thing, we did the hard thing. For this, we had to use Hubble Space Telescope. Because the resolution, you can resolve individual stars much more easily with Hubble Space Telescope. We also have used the Subaru telescope, which is Japan's national telescope. This is a picture of the actual telescope itself. This telescope is terrific fun. The main mirror goes from here to here, right? That's the size of the mirror of this telescope, right? These are amazing, amazing feats of human engineering, right? Of ingenuity. Right? It's baffling to me that we can construct such things, right? I mean, Hubble Space Telescope, it's the size of a bus, right? You can't think, oh, Hubble Space Telescope. No, it's a bus in space. It's really like, what? We can do this? It's terrific. All right, so we use these telescopes, and we map the outskirts of these nearby galaxies. This is a galaxy like the Milky Way. It's a lot like the Milky Way, as it turns out, actually. It's got two relatively big friends. So these are two galaxies about 10 times less massive than this one. And so we put down these little fields. I'll actually show you the picture, right? So this is the picture of that one field that's in yellow. This is the picture. And it's just like, well, boy, Eric, that's really not very good. This was hard. It took a lot of effort. So, but because it's science, you generally just kind of go for just the data you need, and you try not to waste telescope time, because this stuff's expensive. And so that's why it's a little bit kind of fuzzy and grainy looking. And you can see a lot of galaxies in here. And there's maybe a few things that are small, and you're like, ooh, boy, I don't know which ones are stars and which ones aren't. We didn't either, so it took us a while to figure this out. These little red things are things that look like stars at the distance of at the 10 million light years away. And all the other stuff isn't, right? So this is why you actually need a Hubble Space Telescope. From the ground, most of these objects look like stars, basically. It's with the Hubble Space Telescope you can actually tell they're galaxies, etc. So it turns out this is a star cluster around that galaxy. This is a more distant galaxy. It's about 30 million light years away when we discovered it. So this is what we do, is we have to find the red things, so it's a little bit harder than counting. But once we found them, then it's counting. So let me tell you the three main things we found out, and then we will be done. So these are the galaxies we've studied, and including the Milky Way, our own galaxy, and Andromeda galaxy. It turns out that the stellar halos, the outskirts, they vary by a factor of 10 in mass. So these are all galaxies about the same as the Milky Way, yet their outskirts are different by a factor of 10. This tells you that they've had very different growth histories, right? So before we had this expectation, oh, they might be different, etc. We don't know. But we know these galaxies grew in very different ways. Andromeda ate 10 times as much stuff as the Milky Way, despite the fact it's only a little bit bigger as a galaxy. The chemical composition, right? So this is my second chart, and I'm sorry about this. This is the amount of stuff. Oh, it's a log, too. I didn't know I did logarithms to you guys. All right. These are factors of 10 along the bottom, right? So basically here, from here to here is a factor of 10. So this is the factor of 10 range and mass, right? So these are little ones and big ones. That's the Milky Way. This is Andromeda. And the other ones are actually kind of in the middle. And this is the chemical composition. In astronomer speak, we call it iron. It's iron, the ratio of iron to hydrogen compared to that of the sun. You don't have to worry about that. These galaxies, or the outskirts of these galaxies, have very little in the way of heavy elements. These have more. And this red line is what was expected by theory, right? Larger galaxies have more metals. So if you shred them, they should make this shredded mass, right? It's like, hey, look, bigger galaxies eat more broccoli, for example. So I should see more broccoli around big messes from little kids, and we see more broccoli. This is basically what's happening here. And then finally, and actually, well, let me show you another version of this. Remember this map? This red stuff here is from a relatively massive dwarf galaxy that got shredded. That's lots of broccoli. These ones are from smaller dwarf galaxies that had a lot less chemical elements. So you can actually see this not just between galaxies, but in an individual galaxy. The little galaxies that are shredded have lower metallicity, have lower heavy element content than the ones that are bigger, right? So we actually know this in two different ways. So this gives us a way to decode what galaxies made M31 and to decode what galaxies made these galaxies that we have as Milky Way analogs. It is, my friends, 11:30, so I will finish. If you remember nothing else, remember that 80% of all matter that is dark matter. And that we know kind of what it does, but we do not know what it is or why it does it. Which is terrific fun, right? So, there's plenty of reason to keep on studying science. Dark matter drives galaxy formation, right? This is something that was not obvious to us 40 years ago or even 20 years ago, but now it's really obvious, I think. That the reason why galaxies are here, the reason why planets are here, the reason why stars are here, the reason why we are here is because of dark matter. One other reason we know that dark matter, or that we think dark matter is actually real and exists, is that nothing would have had the time to collapse if you didn't have all this extra mass. That wasn't dark matter. The universe would be expanding too fast, this would have gone poof, and nothing would exist. Stellar halos, the outskirts of galaxies, these are the visible probes of the events that build the dark matter halo. Right? So this is how we might actually be able to observe this. And then finally, we've started, so we've not figured this out yet. Right? This is the beginning of the process, not the end of the process. But we do realize that these stellar halos, they show very diverse histories of growth for galaxies like the Milky Way. This is really important. We'll be able to figure out in all these different ways, how do you end up with something that's almost the same at the end? Right? It'll be very, very important to figure out. So I want to leave it there. I want to thank you for your time and for your attention. And yeah, and go blue!